All right. So starting with our deformation of solids. All right. When we are talking about deformation of solid, we're basically talking about deformation of our material that has the ability to compress and that has the ability to extend. We are basically talking about our springs, right? Your springs have the ability to be compressed and they have the ability to become stretched. That is what is we already know. Now, when we talk about deformation of solids, we have to go over Hooke's law. Now, I know you guys have studied Hooke's law in your IG as well. So why don't you go ahead and let me know what do you guys remember, or what do you guys actually, what did you study about it in your IG? What is Hooke's law?
F is equals to kx.
Okay, that's our equation. What else? What else do we remember?
Force is or the weight or force is proportional to the extension in a spring until its limit of proportionality is met.
Yeah, okay, good. And what else?
After the limit of proportionality is crossed, the spring doesn't comply by Hooke's law and is deformed.
Exactly. Okay, good. And anything else? Does anybody remember anything else? Think about it for a second.
I'm not sure, but I think after the limit of proportionality is met, the spring will first of all it's like if the weight is attached to it and the weight has caused the spring to deform and like cross the limit of proportionality, the graph will cause, like in the graph, the extension will increase a lot first and then it will reach a constant as it can't extend anymore.
Yeah, okay. So let's, okay, good points. Okay. So when we talk about Hooke's law in basis basically says to us that the force and extension are directly proportional to each other up till the limit of proportionality, or up till the elastic limit. All right. So let's go ahead and start with it. When you are talking about a string, okay, and when you are adding load to a string, load means weight, right? When you're adding weight or load to a string, the length of the spring is going to increase, which is what we call extension. Now, when we talk about extension of a spring, the spring is going to extend up to a certain limit. When you exceed that limit, when you put more load that exceeds the elastic limit, the spring is going to deform permanently. And that is going to be your permanent deformation. So below the elastic limit, whenever you're going to remove the load, the spring is going to return back to its original position. That is elastic change. That is what is known as elastic change, that the spring is returning back to its original position. But when you are going to talk about your permanent deformation, in permanent deformation, after you remove the load, the spring will not return back to its original length. It is going to have some, it will return back a little bit, but not back to its original length. This is what the graph looks like. As we can see from our up to a certain point, force and extension are going to be directly proportional to each other. Now, this is known as the proportionality limit. When I'm going to talk about my graph, hold on, when you talk about it, there are 2 points. One point is known as the point of proportionality. Point of proportionality is the point at which the force and the extension below it, force and extension are going to be directly proportional to each other. After the point P, this is point P, the point of proportionality. After this, we have another point, and that is just a little bit ahead from the point of elastic potential, and that is known as your elastic limit. So your point of proportionality and your elastic limit are not the same. Point of proportionality is going to be when your force and extension are directly proportional to each other. When you talk about your elastic limit is just actually a little bit ahead of the point of proportionality. And so after elastic limit is that particular limit after force and extension are no longer proportional, but you still don't have permanent deformation. After you cross elastic limit, you are now going to have possible permanent deformation. So point P is the limit of proportionality. Point E is a little bit ahead of it. Elastic limit is that point after which you have permanent deformation. So your point of proportionality or your proportional limit is where you have proportionality, where force and extension will be proportional to each other. A little bit after that, not that much, a little bit after that is the elastic limit. So you will see permanent deformation after the actual elastic limit. So it was only so it is only after you cross the elastic limit that the change is going to go from elastic change to plastic change. So that is one thing that we need to know about it. So that is our force is directly proportional to extension. Now, when we are going to look into our graph, force and extension, this particular graph, we need to look at the gradient, okay? The gradient of your force and extension graph is going to give you your spring constant, okay? So the spring constant can actually be determined by the force and extension graph. The formula we can get is F is equals to KE, and that is what Zoya told us, F is equals to KE. So your spring constant, and how do we define spring constant? Spring constant is force per unit extension. The force per unit extension is your spring constant, and the unit for spring constant is Newton upon meter. So this is how what we know about our Hooke's law. So this is Hooke's law that we had already gone over. So Hooke's law basically states that provided that the proportionality limit, the point of proportionality is not exceeded, the extension of a body is proportional to the applied. That is Hooke's law. So now we know, we studied in IG that it's elastic limit. Now we know a little bit more that proportionality is up to the point of our up to the point of proportionality. After that, we actually have our elastic limit. So elastic limit is the limit after which you actually see plastic deformation or permanent deformation. The gradient of your force extension graph is going to give you the value of your K, which is going to be known as your spring constant. So these are certain pieces of information that we can go ahead and we can deduce from our force extension graph and from our Hooke law. Any confusion so far? Does anybody want to ask anything? Yeah.
Yeah. Can you define limit of elasticity and limit of proportionality? Like once again, like differentiate between them both.
Limit of proportionality is that limit at which force and extension will be proportional to each other. So that particular point up to which force and extension are proportional to each other, that is limit of proportionality. Elastic limit is that particular point after which your spring is going to be permanently deformed. So once you cross the limit of proportionality, the deformation does not take place immediately. You still have a little bit of leeway. It is after you cross the elastic limit that you have the permanent deformation. Were you asking something, Zoya?
No, miss, thank you.
All right, so that is what we know from our Hooke's law. Now, so we have 2 points. Okay, now later on we will also go over certain other points as well. Now we need to go over something else that you can find out from this particular graph. Does anybody know? So I already told you one piece of information from the graph is gradient, which is going to be equal to your spring constant. Does anybody, okay, by the way, spring constant is going to be specific for certain materials. Okay, so spring constant is something that depends upon the type of material you are using. Just like resistivity, if you remember from IG, it would depend upon the type of material. So spring constant is going to be same for the same type of material. So that is what we know from our graph of force and extension, right? So okay, one thing we can get from the force and extension graph is basically our spring constant, that is going to be K. And I said spring constant is going to be force divided by extension, and spring constant can be measured in Newton per meters, and we can get it from the gradient of the graph. Does anybody remember from their IG, is there some other piece of information we can also get from the graph? Does anybody remember, or does anybody know? Can we get another piece of information from this graph?
Oh, we can get the strain energy, I think.
Yeah, exactly. So the force and extension graph, the pieces of information. Hi, Amal, how are you?
Hello, Miss. I'm fine. How are you?
How are you doing, Amal?
I'm doing fine, Miss. How are you?
I'm good. Okay, Amal, so today we had just started a new topic. We had started deformation of solids. Okay, so we were just going over Hooke's law. That's what we have discussed so far. So Hooke's law, I told them that force is directly equal to extension. You have done this in IG, so we were just going over that. So the new piece of information that you need to go over is that on our Hooke's law, we have 2 points. Okay, one point is known as the limit of proportionality, and the limit of proportionality is that point to which force and extension are directly proportional to each other. So that particular point up to which force and extension are directly proportional to each other, that is known as limit of proportionality. After limit of proportionality, just a little bit after it, we have another point, and that point is known as the elastic limit. Elastic limit is that point and after which we see permanent deformation. So that was what we had covered, and we had talked about the fact that the gradient of the graph is going to give us the value of K, which is going to be known as our spring constant. Our formula is F is equals to KE, where K is our spring constant, and we can find it with the gradient of the graph. Now, in our graph, the second piece of information we can get is going to be strain energy. What is strain energy? The other terminology of strain energy is elastic potential energy. Elastic potential energy is energy stored in a body due to change of shape. Energy stored in a body due to change of shape, that is known as your elastic potential energy or strain energy. So both of them are the same thing. And when we are going to talk about it, when an object has its shape changed by forces acting on it, the object is said to be strained. Work has to be done by forces to cause this strain. So when you're talking about, for example, a spring, you're stretching a spring, so the load has to do a certain work to cause this strain, provided that the elastic limit is not exceeded. Provided that elastic limit is not exceeded, the object can do work as it returns to its original shape. So this is your spring. You applied a force next to it and it got stretched. Now, when this weight is doing work right now to stretch the spring. When I will remove the weight, the spring will return back to its original shape, provided that I do not exceed the elastic limit. So when the spring will be returning back to its original length, when the spring is going to be coming back to its original length, that is the energy that it is going to use is going to be known as your elastic potential energy or strain energy. So when you're stretching the spring, you are storing energy inside of it. You are storing strain energy inside of it. You are storing elastic potential energy inside of it. And this is the energy that the spring will use to come back to its original, length. So when you're stretching this string, you're storing energy, elastic potential energy. And when you remove the load, this is the energy that the spring will use to come back to its original shape. Now we can go ahead and we can find out the energy, strain energy, by using this graph, by following area under the graph. Area under the graph is going to go ahead and it is going to give you your strain energy. So strain energy can be calculated by simply finding the area under the graph. Now let's go ahead and take a look at our formula. What will be the formula for strain energy that we can go ahead and use? Now, work done is equals to force into extension. Okay, work done is equal to average force into extension. So average force, we can write down average force as force upon 2, right? If I want to find out the average force, I can divide the total force by 2, whatever my total force is. I can divide that by 2 and that would be my average force. So if I multiply by force with extension, the formula work done is force into distance. That is what we know from our IG, force into distance. Our spring, when it is being extended, it is covering a distance. So technically we're using the same formula. It's just that we're writing down extension because the distance moved by the string is known as extension. So force into extension is work done, and we are going to take average force. Average force is going to be force upon 2 multiplied by your extension. Now we know force is equal to KE. We just came up with the formula. The formula for Hooke's law is force is equals to KE. So instead of writing down F, we can write down KE. We can substitute KE instead of writing down force. Our formula becomes work done is equals to half KE multiplied by E. And the total formula becomes work done is equals to half KE square. So this is how you're going to go ahead and figure out the formula for your work done. So this is the formula for your work done. And since work done and your strain energy are the same thing, since strain energy, your energy and work done have the same formulas, so the formula for energy is going to be half KE square. So this is the formula for strain energy, half KE square. And when you're going to talk about it, you're going to use area under the graph to actually calculate your strain energy using your force extension graph. Any confusion? Does anybody want to ask anything?
No.
Everyone, all clear?
Yes.
Yeah, miss.
All right. So there are two formulas for strain energy. Okay, remember. One is half Fe and the other is half Ke square. So these are the two formulas. All right. So, okay. Now let's go up ahead and talk about something. No, not this. Yeah. Now let's go ahead and talk about something that's known as Young modulus. I don't think this is something you guys have done at IG. I think this is going to be something that's going to be newer for you. Have you guys done Young modulus in IG?
I haven't.
Okay, yeah, I don't
No,
think
we
so.
haven't.
Yeah, I don't think anybody has. So this is going to be completely new for you guys. Now, before we do Young modulus, we have to figure out what is strain and what is stress. What is strain? The definition of strain is fractional increase in the original length of the wire. So you're seeing the increase in the length of the wire and you're turning it into fraction. You're taking the increase in the length of the wire and you're turning it into a fraction. So the formula is extension divided by original length. Whatever extension you're seeing, you divide it by original length, that will give you the strain. Strain has no unit because this is extension. Extension will also be in meters and the length will also be in meters. So they will cancel each other out. So strain is not going to have any unit at all. And the formula for strain is going to be extension upon original length. This is strain. Now, we have another terminology that is stress. What is stress? Stress is force per unit cross-sectional area. Force per unit area. We have heard the same definition somewhere else, haven't we? That is also the definition of pressure. Pressure is force per unit area. Stress is also force per unit area. That is why the unit for stress can also be Pascal. So when you're writing down the unit for stress, you can either write down Newton upon meter square, or you can write down Pascal. It is up to you because the formula for stress and pressure is similar. Stress is force per unit area. Formula is stress is equals to force divided by your cross-sectional area. And the unit is going to be either Newton upon meter square, or you can say Pascal, whatever you want. So that is stress. Now, what is Young modulus? What is Young modulus? Young modulus is going to be, hold on one second. Do I have this graph? Yeah. What is going to be Young modulus? First of all, this is the graph of stress and strain. Okay, this is the graph of stress and strain. And as you can see over here, we have stress on the y-axis and strain on the x-axis. So you can see that your strain and your stress, they are also directly proportional to each other until you reach the limit of proportionality. When you until you reach the limit of proportionality, both of them are going to be directly proportional to each other. Now, we can find out something that is known as Young modulus. What is going to be Young modulus? Young modulus tells you the stiffness of a certain material. Stiffness of a certain material is going to be known as your Young modulus. So Young modulus is, once again, it's like resistivity. The value is going to be specific for different materials. So what is the stiffness of the material you're using? You have a spring, you have a steel spring. What is the stiffness? You have a copper spring. What is the stiffness? That stiffness is known as Young modulus. And how can we calculate the Young modulus? Our formula is stress over strain. So you take your stress and you take your strain and you find the ratio of it. And when you find the ratio of it, that is going to basically be known as your Young modulus. So this is basically your stress over strain. Now, when we are going to talk about our Young modulus, the unit of Young modulus is the same as stress. So the unit of stress was Pascal or Newton meter square. So it's going to be the same. Strain has no unit. So the unit of Young modulus is the same as the unit of stress. And Young modulus is going to be stress upon strain. Now, when we are going to talk about it, your stress strain graph, if you have a stress strain graph, you can simply go ahead and find out the value of your line by finding the Young modulus, by finding the gradient. By finding the gradient of the line, you guys can go ahead and find out the Young modulus. So if you have a stress strain graph and they go ahead and they ask you, find out what is the Young modulus, so just look at the gradient. By finding the gradient of the line, you can go ahead and calculate whatever your Young modulus is going to be. Any confusion? Does anybody want to ask anything?
No.
All right. So that is basically what we had to know about our topic of deformation of solid. Now, let's go ahead and take a look at few past paper questions on that topic. Just give me 1 second. All right. Okay. First of all, actually, hold on. 1 minute. Let me just go over the different materials and the different sort of graphs you can have. So you can have different sort of materials. You can have materials that are ductile, that are brittle, and that are polymeric. Okay. So when you talk about ductile materials, we know what are ductile materials. Does anybody want to go ahead and tell me what they are?
Materials that can be rolled into wires.
Yes, exactly. Your metals are ductile and malleable. That is what we know, right? So your ductile materials, generally they have a graph that looks like this. I'm making the stress and strain graph, not the force and extension graph. I'm making stress and strain.
Miss,
So
are
this
you
is
sharing
stress.
screen?
Yeah, can't you see?
No. Wait, let me rejoin.
Can the rest of you see, or can no one see?
I can see it.
I can see it.
Okay, Miss, give me 1 second.
Yeah, try rejoining and
Okay, now I can see it.
right? Okay, all right. So we have majorly certain different types of material. So we have our graph. We have certain materials that are known as ductile, and then we have certain materials that are known as your um brittle. So when we are going to talk about it, you have ductile materials that we know they are able to undergo certain degree of deformation. They are able to undergo certain degree of deformation without breaking, right? We know they're able to withstand certain degree of deformation without actually breaking. Those sort of materials, they are known as your ductile materials. And then we have our brittle materials, right? Brittle materials are those materials that are not going to be able to withstand anything at all. We have those particular materials that, you know, they are going to fracture really easily. So when you draw the stress and strain graph over here, so this is what the type of shape you will see for ductile material. For ductile material, you are going to basically end up seeing something like this. You can see that this is the point at which you will observe the fracture. And this is the point at which your ductile material is actually going to be able to fracture. So you can see that it can withstand a lot of stress and a lot of strain before it is actually going to go ahead and it is going to end up breaking. So, and this one is for the ductile material. Your ductile material is those material that, sorry, that is your brittle material. I'm very sorry. This is brittle material. Brittle material is that material which is going to only be able to withstand a certain stress or a certain amount of strain before it is going to fracture. Before it is going to break, it is only going to be able to withstand a certain amount of stress and a certain amount of strain. So that is the two types of materials that you have. We have another type of material that is known as polymeric material. Let me show you. That was the stress strain graph. Now let me draw the force extension graph. Okay. This, the first one. Then we have our second one, and then we have our third one. This one is going to be the brittle material. You guys can automatically see that this is your brittle material. Why is it your brittle material? Because as you can see, it is only able to withstand a certain degree of force before it is going to end up breaking, before it is actually going to be able to get permanently deformed, or before it will actually fracture. So brittle material absorb very little energy before they can actually fracture. An example of this would be your glass, your concrete, all of them, right? Then when we talk about our next one, this is basically your ductile material. We have already discussed this. Ductile materials are your metals, copper and steel. And this last graph that you can see, this is for polymeric materials. What are your polymeric materials? Plastics, rubbers, elastomers, all of those are basically your polymeric materials, your polymers, your plastics, your PVC, your all of that you've studied in organic chemistry, the polymers, they are basically your polymeric material. And polymeric materials have no linear relationship on a force extension graph. So you can see this is a curve. At no particular situation do you see a straight line. Why? You don't see a straight line because they have no proportional relationship on a force extension graph. They do not obey Hooke's law. Why? Because they have their composition. Going a little bit into chemistry, we know that polymeric materials have long polymer chains. And these long polymer chains are the reason why your polymers are not following the Hooke's law. So these are the three materials that you guys need to go ahead and actually take a look at. So now that that is out of the way, I hope there's no confusion related to that.
Yeah.
Everyone, is that clear? The materials that we have and the graphs you will see?
Miss, the
Yeah.
polymer material withstands the most stress.
Which can stand the generally ductile material.
Okay.
Miss, when it
Yeah.
comes to exams, do we have to like be able to identify which graph is for which material?
Yeah, you can see that is the reason. Look at the first question over here. Figure 3.1 shows variation with tensile force of the extension of the copper wire. State whether the copper is ductile, brittle, or polymeric compound. So this is what they're going to do over here. They give you the graph and then they ask you to identify based on the shape what type of material you are dealing with. That is why I went ahead and added that for you as well. So looking at this graph, what do you guys think? What material it is going to be?
Ductile?
Brittle.
Ductile,
Oh,
obviously, right? It's going to be ductile. Brittle material is going to fracture really easily. So it's not going to go all the way here. It will simply, if you look at a brittle material is going to fracture very easily. It will fracture over here. That's it. It will be broken. It will fracture really easily. Okay. This is a ductile material. And secondly, they also gave you the name over here. They told you copper. Copper is definitely a ductile material. We know that. So we don't have to get into it. On figure 3.1, mark with letter L the point on the line beyond which Hooke's law does not apply. So can you guys mark a point over here on the screen after which Hooke's law does not apply? First of all, what point is it going to be? How are we going to name it?
Limit of proportionality.
It is going to be limit of proportionality. Okay, guys, I think you're actually maybe mark it a bit over here. Somewhere over here would be a bit better because around here you're still getting a bit of a curve. So try to make it as much on the straight line as possible.
Okay, makes
Try
sense.
to make it, try to make it as much on the straight line as possible. I would advise always put a ruler next to it and then see. So that particular point, you can see you're getting a little bit of curve over here. So somewhere around here would probably be your limit of proportionality. So always go ahead, just put a ruler and see that particular point up till which your line is straight is going to be your limit of proportionality. After which you start seeing a little bit of curve, that is going to be your that is going to be your then elastic limit. Okay. State how the spring constant for the wire may be obtained from figure 3.1. How can you obtain the spring constant?
Or find the gradient of the graph and inverse it.
Yes, good job, Divinsha. So we know that K is equals to force over extension. Over here, the graph is different. We have extension on the x-axis and extension on the y-axis and force on the x-axis. The graph I showed you guys was the other way around. The graph I showed you guys, force was on the y-axis and extension was on the x-axis. So you could directly take out the gradient and find out the spring constant. But over here, the graph is other way around. Extension is on the y-axis and force is on the x-axis. So if I take out the gradient of the curve, this particular line, I will get extension upon force. That will be my gradient. My gradient will not be force upon extension. It will be extension upon force. So to convert this into my spring constant, I will have to inverse it. I will have to inverse it. So it ends up turning into force upon extension. Making sense?
Yes.
Amal, Soya, making sense?
Yes, miss.
Yeah.
All right, now they're saying a copper wire is fixed at one end and passes over a pulley. A mass hangs from the free end of the wire as shown in figure 3.2. The length of the wire between the fixed end and the pulley is 2.5 meters. When the mass on the wire is increased by 6 kg, the pointer attached to the pulley, hold on. I think this will actually be, I think this question is actually linked to another topic. So this might be just 1 minute. Let me run through it. I think this is linked to another topic. Yeah, this is linked to another topic. So let's not do this. Let's just. A glass fiber of length 0.24 meters and area of cross section 7.9 into 10 raised to power negative 7 meters square is tested until it breaks. The variation with load F of the extension X of the fiber is shown in figure 4.1. State whether the glass is ductile, brittle, or polymeric. What do you guys think? Ductile, brittle, or polymeric?
Brittle.
Yeah, it is going to be brittle because as you can see, it is not undergoing any plastic deformation. It is immediately fracturing. It is immediately breaking. It is not undergoing any plastic deformation because remember, you are testing it until it breaks. So that means it broke over here without undergoing any plastic deformation. So this is definitely going to be your, what do you call it? Your brittle material. Good job. Use figure 4.1 to determine for this sample of glass the ultimate tensile stress. What do you guys think? What is the formula for stress? Does anybody remember?
Force divided by cross-sectional area.
Good job. You have your force and you have your information. You have everything. So can you guys go ahead and calculate?
Is it 7.5 into 10 to the power of minus 7?
Minus 7 or
Minus 7?
something? Huh?
Yeah, minus 7.
Are you sure you're getting minus 7?
Yes, miss.
Try again. You should be getting plus 7. So you will do force per unit area. Force per unit area is going to be equal to your stress. Your force is 60 and you will divide it by 7.9 into 10 raised to power negative 7. So the answer I am getting is 7.5, which I'm rounding off to 7.6 because it's 7.59. The answer I'm getting is 7.6 into 10 raised to power 7 plus 7, not negative 7. Are you guys getting the answer?
I'm still getting -7.
Okay, what about anybody else? Are you guys getting the answer? Devinsha?
Oh, I didn't have my calculator, so I just wait 1 second. I was like looking for my calculator.
Okay, all right. Amal, are you getting the answer?
-7.
Are you also getting -7 or +7?
-7, miss.
Okay, hold on 1 minute. Let me try again then. 60 when you're putting this, put this in bracket. 60 divided by
I got
bracket
7.59 times 10 to the power like 7.
10 to the power of 7, positive 7,
Minus
right?
7. No, minus 7. It's 7594936.09.
7, 5, 9, 4,
7594936.09.
9, 3, 6, 7. So that will be positive 7.
Right, yeah.
You're going to move it here. 1,
Yeah.
2, 3, 4, 5, 6, 7. So it's going to be +7. If it was 0.00001, then it would be -7. This is
Yeah,
going
my
to be
bad.
+7.
I'm getting the
Yeah.
same answer.
You're also getting 7.6 into 10 raised to power 7?
Yeah, like rounded off. Like I'm getting the same
Yeah,
answer.
yeah, that's fine. This is going to be +7, not going to be -7, okay? -7 would be when you have 0.0000 something. Okay, so that is the tensile strength. Now you guys need to calculate the Young modulus. How will you calculate the Young modulus?
Stress divided by strain.
Yeah, good. That's the formula, stress upon strain.
Wait, do we know the stress or do we calculate it?
You just calculated a stress, right? Ultimate tensile strength, you just solved for it. Yeah. And now you have to find out your Young modulus. What are you guys going to do over here? You have the stress, you actually have to calculate your strain.
Miss, did they mention the area? Oh, yeah, they did.
Wait, they asked the Young modulus, do they ask it at a certain force or?
No, just Young modulus. Young modulus is going to be the same. Young modulus is not calculated at a certain point.
Because
It's just yeah.
tension over the original length. So won't the extension depend upon the force that we apply?
No, go ahead, take a look at the question. Give the question a read.
Wait, could you just scroll down to the question again? Sorry.
Yeah, over here you won't find anything. I meant over here.
I can just, oh, okay, now it's moved.
Your formula for Young modulus is stress over strain. Your stress is going to be 7.6 into 10 raised to power 7. And your strain is going to be, how do we calculate strain? Extension over
Extension divided by,
original length,
original.
right? Extension, if you read from the graph, it is giving you your 3 into 10 raised to power negative 4. The original length that you have is 0.24. You will divide the two of them and you're going to end up finding out what your strain is. You put that strain over here in the denominator, whatever it is, and you divide stress by strain, and you will find out your Young modulus.
Miss, is it 6.08 into 10 to the power of 10?
Yes, 6.08 into 10 raised to power of 10. Is everybody getting the answer?
Oh, yeah.
All right. Aman, are you getting the answer?
Yes, Miss, it was me.
All right. So, okay, Aman, I'm so sorry. My bad.
It's okay.
Okay. The maximum strain energy stored in the fiber before it breaks. So what is the maximum strain energy stored in the fiber before it is actually going to break? Did anybody get the answer yet?
Miss, we have to use the area under the graph, right?
Yeah, area under the graph, exactly.
So is it half into KE square or is it just the area under
You can do half into k square, but you don't have the k. You have the k is spring constant, right?
Yeah.
You haven't found the spring constant, so that is something else you will have to do. You would first have to find the spring constant and then use the formula. So instead of doing that, it's better if you just use the area under the graph, because you already have the graph in front of you. You can quickly find out the area, so that will be faster.
So is it
So you just
62.5?
9 into 9 into 10 to the power minus 3.
Yeah, exactly. That is correct. So basically what you're going to do over here is you are just going to go ahead and you're going to do, this is your triangle, right? So you're just going to use the formula of area of triangle. So you're going to go ahead and you're going to do half into base. Your base is going to be
Divyanshu,
60
what was your
and height.
Sorry?
what was your answer?
I got 9 into 10 to the power minus 3.
Yeah, okay.
So that is going to be the answer. 9 into 10 raised to power negative 3, and unit is going to be joules. So that is how you're going to calculate that. Then they're saying a hard ball and a soft ball with equal masses and volumes are thrown at a glass window. The ball hits the window at the same speed. Suggest why the hard ball is more likely than the soft ball to break the glass window. So what do you guys think?
Is it because the hard ball will put more pressure on the glass? Like
Why
at a
will it put,
certain,
why will it put more pressure on the glass?
because
It's
the
you're throwing it at the same
molecule-
speed.
same speed, the molecules are all close together, so it'll put more pressure in a smaller area, and then the glass will break.
They have equal masses. They
Is
both
it-
have equal masses and they've equal sizes. So yeah.
If it's hard, will it have a lower tensile?
Okay. If it is hard, it will not deform as much as the soft ball. The soft ball is going to deform more. The hard ball is going to deform less. So what will happen is both of them have initially same amount of kinetic energy because they have the same speed. When the soft ball is going to hit the glass window, it will deform. So the kinetic energy is going to change into strain energy. But for the hard ball, since it is not going to deform that much, the kinetic energy will change into strain energy very less. A very less portion of the kinetic energy will actually turn into strain energy. So the ball is going to have greater kinetic energy compared to the soft ball. And that is why it is going to do more damage compared to the soft ball. Making sense?
Miss, can you repeat?
Yeah, the hard ball is not going to deform as much as the soft ball. So when the soft ball is going to hit the window, most of the kinetic energy will be turned into strain energy. But when the hard ball is going to hit the window, since there is not that much deformation, it will retain most of the kinetic energy, and that is why it is going to be able to break the glass window. A bit more clearer now?
Yes, Miss, thank you.
All right. Any confusion? Zoya Devinsha, all clear?
Oh,
Yeah.
yes.
All right. Okay, guys. So we are going to stop this over here for today. And we are going to continue with questions on the topic of deformation of solids in our next class. All right.
Thank you, Miss. Bye.
All right. Thank you so much, guys. Yeah.
Yes, Miss. Bye.